Notacon.
Okay, I'm Eldon Goldenberg, and
I'm Sean Sujek.
we're from the Dynamics of Adaptive Behaviour Lab at CASE up the road, and we're going to talk about basically what we do for a living. We're both PhD students, and our field is sort of called AI. I prefer to throw qualifiers in, things like biologically inspired AI, but basically we're going to talk about what we do. So, to begin with, I should probably address why I'm so uncomfortable with the term AI. So, we have this 1960s term, artificial intelligence, that sounds, even before Spielberg made a film about it, it sounded like it should be the title of a Spielberg film. I think it gives people images like this. We have our cyborg who's half man, half machine, and I will never get up and say, this is impossible, because that's just begging to be proven wrong. But what I will say is that that's a very, very long way from being a practical reality. So just to make the point, we are not talking about androids or cyborgs or, making artificial people. Instead, we're talking about things like this, which on one level, I guess, are less glamorous and less exciting. But this, in case you haven't already heard about it, is the Roomba. It's an automatic vacuum cleaner. It sounds like it would actually make a passable electronic pet as well. The point, basically, is it drives itself around your floor. You just set it off, and it goes up and down the room, and when you come back, it has cleaned up your floor. And that's a much more realistic AI innovation. Obviously, there's no way we talk about it being intelligent in the sense of doing human intelligent tasks or having a conversation with your Roomba. If I get home and I find someone having a conversation with a Roomba, I'm going to be pretty disturbed. But it's intelligent in the sense that it's not a machine that just has to be directly controlled. It's much more independent. You can give it a task and let it get on with it. Which, if you think about having a person clean your room, that's what you do. You don't tell them exactly where each bit of dust is. You say, clean this room, and you leave them to it. Now, before I let Sean tell you about all the good things we do, it's worth addressing the things that we don't do, that still are within the field. And they tend to get referred to by the rather disparaging acronym of GOFI, which stands for Good Old-Fashioned AI. It's one of those goods that's not really very sincere. And this is what people were doing in the 1960s when they first started using the term. A few things I like to think of it as are AI through search. The best example would be something like a game of chess. In theory, from every chessboard, you can search through the tree of all the possible moves you could make, all the moves your opponent can make in response. Keep searching through it like that and figure out, okay, so which of these moves gives my opponent the least good moves to make? Or alternatively, AI through flowchart. Don't read out the details, I just plagiarized that from someone's lecture notes. But it was very much based on this idea that you do box A and then you can move on to doing box B, and this is the nature of intelligent behavior. It's very focused on what I'd call higher mental processes. The higher should always be in scare quotes, but to give an example that we're going to come back to a few times, they weren't interested in how we walk, because until you give that serious thought, walking down a room seems like a trivial, obvious problem. They were much more interested in, well, how do we plan chess moves, or how do we debate philosophy? Then this is an example of the Turing test, which was the gold standard for good old-fashioned AI. The idea was basically that you have a person communicating with an entity that they can't see, so you get around issues of, well, it's made of metal, of course it's a machine. They're just communicating by text, so it's almost like you're IMing this other entity, and you have to decide whether it's a person or a machine. So a machine that passes the Turing test is one that fools a good proportion of human beings into thinking they're actually talking to a fellow human being. And I think that's illustrative of the kind of things that GoFi was trying to achieve. And finally, some of you might recognise this. Bonus points at the end if you can tell me what movie Whopper came from. I'm hoping you all can. But the point I wanted to make with this, in line with the Turing test, is that if you look at that, it's a disembodied machine. It's just this big lump of electronics, with no thought about the importance of the body, which is why the Turing test had to basically cheat by saying, we're going to communicate on text only. They were avoiding all these other problems of what we have. Now, I do have a habit of being quite disparaging about all of this, but it was all the product of its context. My background originally is psychology, and I don't want to turn this into a psychology lecture, but basically it reflected the psychology that was dominant in the 50s and 60s. And this was revolutionary at the time, because prior to the 1950s, people didn't even, as psychologists, look at mental contents. They just looked at behaviour. It's all the famous rat in a maze type experiments. And what happened in the 50s and 60s is there was what they called the cognitive revolution. People finally said, well, how can you have a science of the mind that doesn't actually study the mind? And they started looking at trying to understand what a thought process is. The problem was that this is, the most complicated thing we can look at in ourselves. So what they started doing was, at least looking at modern terms, pretty naive. It was basically psychology through flowchart. This, as it happened, is a recent example, and it's a little cruel. A friend sent me this from his PhD advisor's published work. But the key point is that when you start trying to make a flowchart of any sort of thought process, you get things like this, where you have a box, I don't know if you can read it from the back, but it just says, Process 7, with nothing about what Process 7 is. And what basically ends up happening is caricatured in this. There's all these gaps, and they don't really cover anything. And that basically set up GoFi to have its problems, because all of the gaps in the models become things that your AI can't do. But before I leave it all together, I should acknowledge that there are things this did well. And a point I really want to stress is that I'm not trying to argue that GoFi is a waste of time and should be thrown out. It tries to accomplish completely different things from modern biological AI. So one example would be medical expert systems. I don't know how widely these are actually used, but they're the textbook example in academia. Basically, the doctor has a script that says, ask questions X, Y, and Z. And based on the answer to the first question, that's entered into a computer, which goes through a decision tree and says, okay, this person's running a fever, that cuts out half of the things I might have wrong with it. Narrow down to this half. And within that environment, it works pretty well, because there's a human interacting with it, who has that expertise, and the domain is relatively limited. Although there are unlimited things you could have wrong with you, there's a finite set of diagnoses the doctor can give you, treatments the doctor can recommend, so it can all be covered. And the one practical example I know is that in Britain, the National Health Service has this website called NHS Direct, which you can go to, and it will basically say, oh, you're sneezing but you're not running a fever, you have a cold, don't waste your doctor's time. But what you see in terms of limitations is that actually it very often says, this may be important, go and see a doctor. So it still has to defer to humans with experience for anything serious. The next one is theorem proving. Theorem proving is something I got very tired of last year, because I had to go through the computer science PhD qualifiers. The point is that it's a human behavior that actually does operate by applying simple rules, although they may not seem obvious to the grad student studying for quals. There are rules that underlie it all, and you can codify those rules. So GoFi was pretty successful with that. The paperclip, I'm expecting to get hassled for this basically, but that paperclip that drives most tech-savvy users of Microsoft products insane is actually really useful to my grandma, who's a bit afraid of computers and doesn't really know what she's doing, but wants to. The way that works is what I'd call old-fashioned AI. It looks for specific set things. So if you have dear and a name and then a comment, a new line, it looks like you're trying to type a letter. But at the same time as saying this is useful and a success, one of the reasons why it is so irritating is that it's extremely unsophisticated. So it doesn't have any way of responding to, okay, this user always sends me away, I'm not going to pop up and bother them anymore. Or, this user looks like they're writing a letter when actually they're doing task X instead, I'll change my response. And finally, to game players. I used chess as an example before because it's probably the most high-profile success of GoFi. I don't know if you recognise the thing, but you probably recognise the name. This was IBM's computer chess player. This did work more or less as I caricatured in terms of searching the space of possible games. And the problem is this in the late 90s, and it's a thing that took 8 years of development and weighs 1.4 tons, because even for the game of chess, it had such a gigantic space of things it had to be able to examine. So it had to have huge amounts of memory, huge amounts of storage, and utterly state-of-the-art processors, many of them running in parallel, to be able to compete with a human being who just has what's in here, and obviously can't proceed by expanding all the possible moves. By contrast, something like Go, we don't yet have a good computer player for, because the space of moves is just that much bigger. And I'd say that the biggest problems that GoFi has are in dealing with the real world. Chess is great if you want to work with GoFi because it's constrained. However big the space looks like to me as a not very good chess player, it's still limited. There are only certain moves each piece can make, and there are set ways the game ends. Where GoFi really fails is if you have things that have to have some kind of physical instantiation. So these two are a robot called Shaky, because that describes how it moves, and a computer program called Shurdlu, which apparently just came from someone hitting keys on a keyboard. They were both supposed to be demonstrations of how you could communicate in natural language with an artificial system, and it would go and do your thing. So you would say to Shaky, walk across the room, and Shaky would go, and Shaky will... I shouldn't go now, I'll get feedback. Shaky will walk across the room, and Shaky wouldn't have realised that it would get feedback, so Shaky would have carried on. Or you say to Shurdlu, pick up the red block. And Shurdlu moves along its arm. It's like one of those things in fairgrounds that you try and win the cuddly toy to impress someone with. So it'll move along and it'll drop its hand down and pick up the red block. But they're incredibly restricted in terms of what they can do. Shurdlu only exists in a world that actually resembles this. It couldn't adapt to this table and say, pick up the pen. And Shaky, for one thing, it has wheels, so a single step will defeat this robot. For another, it's got really limited vision. Now if you look at the picture, and you'll see this on any picture of a 1960s robot, it's got white walls, white floor, no features. If you put Shaky in this room, it wouldn't be able to cope because the carpet has a pattern, and the walls have features, and there are things moving around out of its control. And that would be enough to stop the thing from coping. So, I think the point I'm trying to make is that GoFi has been very useful in restricted controlled domains, but it can't cope at all with the real world, and with simple things like an instruction to walk across the room that seem trivial to us. Now, I'll hand over to Sean to paint something more positive about what we actually do and what works in our world. Thanks. Oh yeah.
All right, so Eldon has just pointed out that GoFi basically has, it's incapable of dealing with the real world. So if you want something that deals with the real world environment with all its complexity, why not look to something such as a blue sky? Something such as this cockroach here that's able to navigate up this flight of stairs made from lucite blocks whose thickness is much greater than the body height of the organism. Yeah, we had a little problem with the video. But you can see with its 6 legs, it's easily navigating up this basically complex terrain. Actually, you can make the lucite blocks even higher, maybe twice the body height of the organism, and it's still able to climb up and over them. And usually this is done very, very quickly. They're pretty impressive to watch, except when you're in your house. But okay, there's an example of something that's able to deal, what we could term a simple organism that's able to deal with a really complex environment. So there's a shift basically to look to biology for inspiration. And if forced to pick like a focal point for this, I'd have to say it was Rodney Brooks' Assumption and Architecture Ideas. And he has a quote here which basically reflects what seems to be an obvious statement, his inspiration, that it is instructive to reflect on the way in which Earth-based biological evolution spent its time. So not only is this saying that look to biology basically for things that do what we want, to solve these technical problems that we want to solve also, but in addition, that this focus that Eldon was talking about with GoFi on higher cognitive processes actually occurred much later on in evolutionary terms and much more quickly. So what we thought as a simple problem, such as navigating a room or basically finding a mate, those things took much longer and are actually very complex tasks in their own right. So for this, an example here, I guess this change in idea. Is yours brighter? Thanks. Okay, the traditional approach basically with this linear processing, in which there's basically a large disconnect between sensory information, this linear progression, all the way to the motor output. Whereas his approach basically has this behavioral modules, in which there's a short connection between sensory information and the actuators, and that these different behaviors do different things. It's a lot more robust. Right. So from this basically paradigm shift to biological inspiration, there was a whole plethora of techniques, design practices, and tools that came about, or even if they were previously worked on, then they were a lot more focused on, became a lot more popular and studied, such as GAs, genetic algorithms, artificial neural networks, the ideas of embodiment and situatedness, and I'll explain each of these more in detail, changes in robot design, the hierarchy of simple behaviors, and then neuromorphic engineering. And we'll just take a little walk through each of these. So for genetic algorithms created by John Holland, back in the 60s, I believe, he basically took 2 mechanisms of modern evolutionary theory. Genetics on one hand here, and natural selection on the other. From genetics, we get the idea of basically heritable variation, in which parents are able to pass on some of their genetic material to the offspring. Okay. Then from a natural selective processes, basically you get differential reproduction, in which some organisms have offspring and some don't. This can be fitness related or even just genetic, something like genetic drift, and we're just a random event. Takes them out of the population. So with artificial neural networks by Warren McCulloch and Walter Pitts, these were created much earlier, back in the 40s, but it's continues to be an active research area, and the models have grown in complexity and focused on different tasks. Their original model basically was from the 1940s neurobiology, in which neurons were thought of as basically just on or off, very, a summation basically of this input. It's very, very simple, in which you have inputs with connection strengths. They get summed, and once the summation passes some threshold, then the state of the output is 1. The summation doesn't pass thresholds, it's 0. And again, nowadays you see compartmental models which actually take into account the biophysics of actual cells, and pretty impressive. Okay, so the idea of embodiment and situatedness, these 2 ideas are represented here with ideas from our own advisor Randy Beer's work, in which if you want complex adaptive behavior, the nervous system resides not by itself, not just removed from anything, but actually within a body that has physical parameters to that. And then in situatedness, the body is actually interacting in an environment to move and actually produce the behavior. And this idea of changes in robotic form, there's been a huge push for biologically inspired robotics. This is Roger Quinn at Case, who has the Biologically Inspired Robotics Lab, and this is one of his robots, R3, which is very strongly based on cockroach that we saw earlier, Blabberus. This basically, it's a scale-up, leg length, and all these things are based solely on the cockroach. The number of degrees of freedom for each of the limbs is based on what you would find in the animal itself. And let me see if this video works. So this video will show actual posture control of the robot. It's just standing there. Its muscles are basically McKibben pneumatics, and so you'll see the guy who built it basically shoving the robot from all different directions, and watch it stay. So you can think of this posture control as one of those behavioral modules, just staying upright. He has another video on the website of which he's actually lifting up the legs, and it's able to shift its body, center of gravity over and remain stable. It's really impressive. Okay, and then kind of building on this hierarchy of simple behaviors, taking like the posture control that we saw earlier, you might have something at a lower level of just even finding a foothold. Okay, and this is Jim and Ding's work at University of Illinois at Urbana-Champaign, and so I'm going to show 6 snapshots of his little insect leg, basically finding this pin as a foothold. 2 servo motors, brings the leg down, and this is going to bring it down into the bar here. Okay, makes contact with it here, but it's farther up on the limb instead of being at its foot. Starts sliding the leg up, and then finally when 5 and 6 makes contact with it and is able to make that a firm foothold. Okay, so I have a video actually that's showing it's really grainy, but it does a nice job of just this 2 degree of freedom leg that's actually able to find this little bar as a foothold. You'll see it make different contacts from forward and then swinging the leg forward or swinging it back. Actually, they'll move the foothold and you'll see it regain it. And this is all basically done by local reflexes, instead of having this go all the way up to higher processing centers and taking time. And again, the foothold is right here. See, it's made contact, regains, whoops, slipped, comes back up, situated, slipped again. And another leg strike, up, and on it. Again, this is all basically, if you have local reflexes controlling this behavior, then you don't have to spend all this processing time to send it up to higher areas. Okay, and the last example of some of these tools is this neuromorphic engineering. This is Timur Horiuch's, a lot of it's Timur Horiuch's work at University of Maryland. He came and gave a talk at Case recently. I had the pleasure of talking with him. It was pretty exciting work. So what he's done is basically created neural models through basically, VLSI technology. Well, created the chips then basically for these. That model then, his system is going to be echolocation in bats. And so he's created chips, or basically, these VLSI chips that mimic a lot of the neural dynamics in the nervous system for echolocation. And I'll talk a little bit more about his work later on. Okay. And Ellen's basically going to show these techniques that I talked about and give some examples of how they'd apply to technological problems.
Okay, so I'm going to start with talking about my master's project, which is, to be honest, probably the least exciting of the applications that I'll talk about, but this is the one I really know how it's done. I'm also expecting some hassle about this later, because what I made was a product that is useful to people who send junk mail. Basically, I was an intern at HP, and they've just bought up this company that do one-off prints at the quality of professional print runs, but at the cost to start up of a laser printer. So, among the application, there's people who are sending out any kind of mail shot. If it's a newsletter or advertising, whatever, they may well have enough information about people it's going to know that, you know, household A is only going to read pages 3 and 4 of this, or only going to look at these 3 items. And now there's the hardware that can actually generate these one-off prints and do personalized mailings. Depending on how you want to look at it, I kept telling myself that what I'm allowing them to do is save a lot of paper. The other side is I'm making it cheaper for them to send this kind of nuisance stuff out. But the problem is that if you just have, let's say, 7 boxes, say each of these is an advert for a product, and you just throw them onto a page, you get something like this. It's not necessarily going to look very good. So the problem is, how do you go to a layout that looks neater without spending lots of time and money with human designers who will do the job well, but remove the whole economic benefit? And the answer that I found was to use a genetic algorithm. So basically we have a population of strings, each string being a representation of some kind of layout for the given document. And you go through generation after generation, mutating descendants, and then comparing them all in some way that can be objectively measured. So in this case, what we actually did was selected the ones that wasted the least space. The rationale being that it's pretty hard to codify what is a pretty design. But if you take this and then add some space evenly, it will at least look tidy on the screen, whereas this is something of a mess. And the big issue with this kind of thing is that it can be approached as a search problem. I mean, a genetic algorithm for something that's in a restricted domain like this is basically a search algorithm. So the question is, why not just do a dumb search? And the answer is this figure, which is from the thesis, and it got me some interesting comments, because it's a log scale, and about 3/4 of the way up, you reach the number of atoms in the known universe. And what's actually on it is, as you increase the number of things to be placed, the green line is the total space of things you would have to search if you just wanted to search the blindly. And the red crosses are the number of cycles that the GA has to go through. So you see, for very small amounts of data, it doesn't really matter. But as you go up, it becomes slower and slower, and eventually just outright impossible to do this as a search. And that's why things like genetic algorithms are useful, even in things that don't look like biological evolutionary problems at all. It can be a very efficient search technique. And before I leave this problem behind, I want to point out that it is of more general use than I've made it look so far. It's basically a problem of fitting items into a finite space. They're called bin packing problems as a class. And a couple of other practical uses are laying out a CPU. For one thing, you want to use less silicon so you can fit more chips onto one wafer. For another, the closer the elements are to each other, the more reliable that device will be. Another is packing physical containers. This particular example is a little easier because they are regular things. But let's say you're packing a whole range of different shape, different size objects. So the argument that at least I made in the thesis, and seems to have been well received, is that if you have this technique for doing a document layout, you can generalize it to all these other related problems and pick it up. And that's another important point about the way we work, because on the one hand, having thrown out this sort of flowchart or search idea and said, well, you can't just use the same hammer for every task. At the same time, we're not in a world where we have an unlimited number of different techniques and no clue how to use them. You can very often look at an existing task and say, okay, a similar task to what I'm trying to do has been well solved using this technique. Let's see if I can adapt what they did. Now, an example that I'm particularly fond of for the use of these techniques are the rovers that are up on Mars right now. And they've been in the news this week. I don't know if you heard, but they've actually had their missions extended by another year or so. So they've already run for, I think, a year longer than they were predicted to, and they're keeping on going. But the basic problem is that we have spy vehicles on Mars. I don't know how many of you were in Richard Thiem's talk when he talked about how if you were a farmer on Mars, you'd be seeing UFOs. But basically, we have spy vehicles, and what this is one of the actual rovers. You know, it has a camera and a drill and various other sensory devices, and it's reporting back on what it sees. Now, if I wanted to spy on the talk in that room, it'd be pretty easy. I could stick a camera on a radio-controlled car and I could send it round, and you know, it might get some funny looks in that room, but it would be able to do its job. But there's a big problem with doing this for Mars, which is that of time. If you think about the distance to Mars, I mean, even in the moon landings, there were delays in transmission. Neil Armstrong would say his portentous words that he'd rehearsed for weeks, and then there'd be a delay until it was acknowledged by Houston. Once you get the distance of Mars, this becomes a significant problem, particularly because the distance changes. When Earth and Mars are far apart, I can't remember numbers, but the distance is certain. The time lag for a radio signal is certainly the order of several minutes. So you can't just radio control your thing around. What they had to do instead was set up a rover that can run more or less automatically. So it goes back to what I was saying about the Roomba, that this thing isn't able to just be completely independent. It's not like, you know, James Bond behind enemy lines that will go off for weeks and gather information and finally report back. It's given instructions at least daily. But instead of being move forward 1 centimetre and then turn right 5 degrees, they will be move towards the edge of this crater and take pictures, and these are the kinds of rocks we're interested in. When you see one, drill out some samples. And it has a controller that uses the subsumption ideas, the subsumption architecture ideas that Rodney Brooks is famous for, where at the highest level it has, okay, I want to get 100 meters northwest. Below that there's things like obstacle avoidance, various behaviors to avoid it getting stuck. And with that we have things that are much more useful than a radio controlled car, because it only needs to connect asynchronously. It can get a batch of instructions and send back a batch of data. One thing you might notice after everything I was saying about wheels is that this is another wheeled robot. The ultimate Mars rover, well, I suppose the ultimate Mars rover would actually be an astronaut, but the ultimate Mars rover robot would be one with legs. And there are such things under development. There's quite cool work going on at the moment with robots that can scramble across rough terrain. But it's too new at the moment. They're not reliable enough. We're still learning how to control these things. So that's why it's not used yet, but I expect to see legged Mars rovers in my lifetime. Now, another project that actually a friend of mine did for his masters was credit scoring. Now, if you go and apply for a loan, it can be quite a complicated decision whether to give the person a loan or not. Now, it isn't necessarily. If I apply for a loan, I already know that the bank will tell me, you haven't lived in the US for long enough, insufficient history and a social security number, deny. And there are other people who are obvious good credit and will always be given pretty much what they ask for. It's the cliche of needing to have money to be able to borrow. But for everything in between, it's a fuzzy decision. There isn't a clear rule that can be applied, and this may match some of your experience. There are certainly people who would apply at different banks, and some would give them loans, some wouldn't. Or some would give them preferential rates of interest, some would charge them a lot. So it's dependent on a relatively subjective assessment of risk. And that subjectivity is a problem. This is an area where the demand for automation isn't so much for efficiency. It's because of cases where people will cry out, but that wasn't fair, you only denied me a loan because X. I know back in Britain the controversial thing has been credit scoring by district, where you get problems that because there's a few people who've defaulted on loans in that particular set of council housing, no one else at that address can borrow money anymore. And this doesn't really resolve the problem, but if you use a computer, it's very convenient for the banks to be able to point to a computer system and say, but the system said so. It's applying the rules, and it would have said the same thing whoever made the application based on that data. whereas with a person there are always possible accusations of bias. But because it's basically mirroring what a person does, what they found was that you couldn't write down the rules. If you try and get a bank manager to write down, okay, so what are the rules that say whether someone gets a loan or not, that system based on those rules will give out more bad debt and refuse more good creditors than the bank manager would. So to try and capture the human judgment, they set up a neural network system which was trained using real data. So the thing about neural networks is that basically they do whatever kind of pattern classification you train them to on examples. So in this case it would be given a whole set of people, and the person would have a load of data associated. And with that person it would say, loan granted at interest rate X for amount of money Y, or application declined. And over time it could add things like, this person has defaulted. So it has a way of learning from its mistakes, because it gets input back. And basically it's trained to make the same decisions as the person. One big problem with this kind of system is you can't necessarily make it any better than the person, but you can at least make it as good and consistent. Now on the same kind of theme as the loans, there are all kinds of natural phenomena that are in principle predictable, but difficult to predict, which we can apply this to. So the examples I've got, I'll just talk you through the pictures. We have a kid playing with his own heart. This obviously is after he's had a transplant. We have Hurricane Isabel. Those of you who are local might remember Hurricane Isabel as bringing lots of rain, but if you lived in Florida, it was of much greater importance. And thinking back to this past hurricane season, it would have been very useful for Floridians to have a better idea of where each of those hurricanes that hit them was going to hit, so that they could know which towns need to be evacuated, which towns don't need to worry, and so on. The aftermath of the earthquake in Istanbul about 10 years ago, that one's close to my heart because my grandmother lives there, and she was actually stuck in her house because something had basically fallen on the doorway, so she was stuck for a day. And the eruption of Mount St. Helens, I think this is from the big one in the early 80s, but earlier this year Mount St. Helens was active. You know, the rock was rising, there was steam coming out, it was venting, and there was some speculation of, you know, when are we due for our next eruption? But the problem is, these things are all very hard to predict. So what heart failure and storms and earthquakes and volcanoes all have in common is that although they're difficult to predict, they're not random. They're not even, in the strictest sense of the word, chaotic. They're just very complicated and controlled by things that we don't yet understand very well as scientists. So we can apply things like neural networks to these, because the neural network just trains to fit a pattern. It doesn't need to, quote, understand in the, well, I guess in the philosophical sense, and understanding is a really big minefield philosophically, but the system doesn't need to have some notion of, oh, I forgot to put the picture credits up. It doesn't need to have some notion of, well, this is why the hurricane will hit this town and not that one. It's enough that it just draws out the pattern and says, this is what the pattern is leading to. The neural networks are very useful for all those kind of predictions. And finally, more relevant to here, I want to talk a little bit about computer security. I wish I could remember who did this, but there used to be a Taliban website back when the Taliban was the government of Afghanistan. And one day I went to have a look at it because it's always fascinating seeing what these kind of people say about themselves. And what I saw was this. So obviously somebody has hacked that. And I don't really care if somebody hacks Taliban.af. You know, I have little enough time for what was supposed to be there that actually I was more amused by this than bothered by what I couldn't read. But anybody who runs any kind of computer system has this basic problem of security, which other people have talked about it at Notacon as well, where there's always a conflict between keeping out people you don't want to have access to the system without shutting out those who you do, or making life too difficult for those who you do. And The modern AI approach to this is to look at something like the human immune system, which has to do essentially the same task. If you think about autoimmune diseases, what's gone wrong there is that suddenly the immune system is attacking cells that you do want there. So it's got to make the distinction again between these are the welcome cells and these are the unwelcome cells. So people are trying to apply this. There is a thing called an artificial immune system, which is basically another kind of classifier that tries to roughly model how the immune system works. And again, make that wanted-unwanted distinction. And if you could make that reliably all the time, you could just shut off connections to all the unwanted traffic and reduce the hurdles all the wanted traffic has to go through. At the same time, if you can do that without human supervision, well, your sysadmins get to sleep at night, which is obviously a bonus, and the system is more reliable. So hopefully that's given you an idea of some of the practical applications that these things currently go to. You know, it's not robots that walk and talk, but actually there are some pretty cool and pretty useful things. And now I'll pass you back on Sean to talk about the other side of this transfer, which is what pure science research gets out of us making all these models and playing with them.
All right, as Eldon just said, I mean, basically, how does this return all these basically technologically inspired or biologically inspired tools, technological tools? What does it bring back to the life sciences? I'm going to give 3 examples: one from cognitive science, one from evolutionary developmental biology, and then one from neuroethology. And this is Eldon's work, actually, in the cognitive science area that he's done recently. And the object, or basically, traditionally it's been a very symbolic approach to understanding cognition. And recently there's been this surge of this situated, embodied, and dynamical approaches to understanding these thought processes. And so what Eldon has been working on is basically creating an agent, represented down here, basically that performs a selective attention task. It has to catch each of these 2 falling objects, okay, and it has basically just vision with these rays, and it catches these by moving back and forth. And he's basically implemented this using a neural network, very small number of neurons for this, and a genetic algorithm to set the parameters for this. And this task is, you know, it's minimally cognitive, as I've indicated out by that, basically, that this is a difficult enough task that's of interest to basically researchers in the in cognition. And then through understanding the dynamics of the neural networks, to get an understanding of how this thought process works. So, and Eldon has a nice video. Whoops. Going. There. I must have tapped it. It worked earlier. There it is. Thanks, Eldon. It's on the screen. You can see it's scanning in and basically collecting the other object. Now again, this is a selective attention task, basically, where sometimes it moves out of range of the other ball, it has to remember that I need to go and catch this other one out here. So again, it seems relatively simple, but it's of genuine interest to the researchers in this area. And again, being that it has such a small number of neurons, you can actually get in and look at the neural dynamics and gain some understanding of this, what you think of a higher process. Okay. Briefly, the evolutionary developmental biology example, EVO-DEVO for short. And so earlier I pointed out this modern evolutionary theory showing the 2 components of genetics and natural selection. Well, I left this space out, and recently people are noticing that development is crucial to understanding this. This is like the middle process that's going on. Basically, how do these developmental processes affect the evolution of organisms? And in my own work, I'm investigating how basically developmental bias might affect evolvability. By evolvability, I mean the ability of these organisms to find good solutions and continue to find good solutions to ecological problems. I mean, how do you find mates, and basically how do you, over time with coevolution, are able to solve these problems? And I'm saying that developmental bias, that is this bias in the production of variants of different forms and behaviors, results in evolvability. I have 2 examples here, one population and showing this circle represents the distribution of variance, and that it's pretty uniform, it's non-biased. In this fitness landscape where higher or darker regions are higher fitness areas, you would expect over time for population 1 to move up this fitness ridgeline, and it would take some time. So population 2 then shows a bias in its development. It also moves up the ridgeline, but much faster, and that's basically because you don't have offspring falling off this ridgeline. So I'm saying that if development actually constrains the variation in form that you see, you're actually going to evolve much quicker. And my work involves basically a model of neurodevelopment to try to get at these questions. Okay, and the last example in neuroethology, which is the neural basis of behavior, we're going to take a look back at Timur Horiuchi's work again. Remember, he created the VLSI chips that capture the bat signal processing system. Do you picture the bat? Okay. And so one aspect of the system is basically determining range from an object. So with, you've got azimuth, basically determine the location of an object. You've got azimuth, elevation, and distance off. And so one of his graduate students has basically created a VLSI chip that's based on these delay-tuned neurons in the bat brain that actually codes information of how far an object is. And he's triggered that basically chip to this tail that you'll see right here. And he's going to swing an object at it and basically have the chip trigger the tail to block the approaching object. Dang it. Nope. Ellen? Alright, can you show that again? This is a top view. You'll see the tail. He's got a bottle basically on a string. It swings toward basically his chip and the sensors. And the tail, the tail blocks up or deflects the bottle. And if you can show that one too, which behind the sensor array right here, smack. Okay. So how does this affect actually the biological sciences, the pure science that Ellen was talking about? Well, one, building a model basically points out a lot of the missing details that you don't have from experimental biologists. So many times they're concerned with their own questions and doing their own thing. Then somebody else wants to make a model of it and realize, wait, what about this? Is this connection there? That sort of thing. His work has actually driven the biological experiments. He's worked with a psychologist in these bats, basically investigating the neural basis for this. The second reason why building a model affects the pure sciences is that he's able to interact with the system in real time, and that's really where you get this insight into how this thing works. And hopefully this will eventually allow us to understand basically how they're able to hunt and do all this in complete darkness, such as a cave. Right, and now for our conclusions.
I guess I'll pick up on the technology. The big message I always try and give people if they say, so you do AI, I should be scared, is don't expect to see commander data anytime soon. That's an invention for science fiction purposes. We're more likely to have much more humble innovations. A lot of the real AI products won't be branded as with artificial intelligence, because that's usually your warning sign that actually what's being sold is snake oil. There'll be little refinements to how your car engine runs, or another household robot that automates another task for you.
And the 2 points that I wanted to make, one is with the last 3 examples, that a lot of these AI techniques, such as genetic algorithms and neural networks, are being used in what you would term pure scientific research to gain an insight into these incredibly complex systems. And then last of all, the point I wanted to make was just that Eldon brought this up a little bit earlier. You need to be able to see across your own discipline boundary and basically say that, okay, my ideas can be applied somewhere else, or ooh, somebody's working on something here that actually can provide me some insight into the problem that I'm having. Right, and we can take questions now.
How much time do you have?
Like 7 minutes.
Okay.
Chris?
Well, one thing that this particular system doesn't do is it doesn't recognize, okay, that's going to be out of range, I won't bother trying to catch it. It's a lot more limited than that, because it can only deal with what it was trained on. And everything it was trained on were trials where it could catch both objects. But basically, it has some sensors, those rays that you saw. And then its output is just to a motor, which just takes it to one side or the other. In between, there are what we call interneurons, or a hidden layer, which are neurons that don't have any connection directly to the outside world. And those can basically track. So we're still doing analysis on these things, but what they seem to be doing is that some of them get activated by even very small speed differences. And just in terms of the way they can work, it's a lot like the human brain, in that a very small difference that's big enough to be perceived can actually be picked up on and recognized, even if it's only just perceptible. And that can be enough in the system for it to seize onto one and focus. Then there'll be another interneuron that just activates to say, after catching this ball, turn left. And then it just sort of shoots off left until they can see the other one. I hope that makes sense. The thing is, we don't completely understand the system. Yep. Yeah. Okay, I'll start with the last point. It's just a model. It would be relatively easy to build as a physical system because it is still quite a simplified model. You know, you just have a thing on a track with a few light sensors. But all that would really bias it would slow things down. But building physical models is important when you work in a real complicated physical world. So like if you're developing that Mars rover robot, you don't want to do that entirely in simulation. You need to test that in an actual environment with big rocks and things. They asked about computational power. To actually run, this takes barely anything. It has maybe 20 neurons, and each one just sums a load of numbers and applies one fairly mathematically simple function to them. So it's tiny computing power. But to get it to a point where it does anything intelligent does take time. We have a cluster of old computers in the lab that we use for doing these runs. And that particular system, it takes about 2 days on, I guess, about a 1.5 gigahertz processor to complete an evolution run, which then gives us things that can respond to that. So in terms of practical application, there's much more restriction in terms of how difficult it is to get the system working in the first place than how much power it needs to work. Okay, I'm not sure. Okay, I think we're out of time. If you have any more questions, we'll be drifting around, definitely wanting to be asked more things and talk about this. Yes.